So let's continue our discussion on vectors. By now we have discussed the basic definitions of vectors, the representation of vectors, and our last topic was the angle between the two vectors, right? Knowing all this, we move our discussion further, and let's take up the most important part, which is the addition and subtraction of vectors. Addition and subtraction of vectors. Now, let's say in first cases, let's say the vectors are along the same line. Say this is a vector A having magnitude 1, and say this is a vector 3A having magnitude 3 times that of vector A, right? In this case, the addition of these two vectors or the resultant of these two vectors will be a vector 4A in the same direction as vector A, right? In another case, if this is a vector say 5A, 5 times A, and this is a vector say 2 times A, then the resultant of these two vectors or the net result of these two vectors or the addition subtraction product of these two vectors will be a vector 3A in this direction, right? So we basically need to conclude the resultant of two vectors, right? If the vectors are along the same line, then we can simply add or subtract the two vectors for getting the resultant of these two vectors, right? For visualizing this, we can assume as if the vectors are not only but the force vectors. We can assume the vectors to be force vectors so that we can feel it, and we can assume a mass. Placed here, and let's say taking the first case, say 1 Newton force is acting in this direction and a 3 Newton force is acting in this direction, right? We took vectors A and vectors 3A. So in this case, if we assume that whenever we see a vector, if we can assume that there is a mass placed there, and if we can assume that the vectors are nothing but the force vectors, and if we try to feel the effects of the force vectors on this mass, then we can conceptualize the resultant of the vectors, right? So in this case, the resultant will be a 4 Newton force on this mass. Taking the second case, we had a force of 5 Newton in this direction, and we have a force of 2 Newton on the opposite direction. So the resultant will be a 3 Newton force on this mass, right? So we can actually feel it by assuming a small mass and assuming the vectors to be force vectors applied on the mass, and we can see the resultant of the two vectors on the body, right? Now, in this case, the vectors were lying on the same line, right? And here we can simply add or subtract two vectors to get the resultant of the net resultant vector. So I can conclude that vectors along the same line nearly behaves like a scalar. Vectors along the same line nearly behaves like a scalar. Right? This was the first case of addition and subtraction of vectors. Now, if there are two vectors and they are inclined to each other at an angle theta, let's say there are two vectors which are inclined to each other at an angle theta. If we have two vectors, vector A and vector B, and let's say these two are inclined to each other at an angle theta, where theta is the angle between the two vectors when their tails coincide. I discussed this. Now, this brings up to our parallelogram law of vector addition, our parallelogram law of vector addition. If this is a vector A and this is a vector B, and theta is the acute angle, or theta is the angle between these two vectors, then in this case there will be a vector C. There will be a vector C, which is known as the resultant, of vector A and vector B. This means that this vector C is the single vector which can produce the same effect as produced by A and B together. For example, for visualizing this, again I can assume a small particle here. Say I have a small particle here, say of mass small m, right? Visualize a small particle here, right? Or visualize a person is standing here, and there are two forces acting on the person or that mass. There are two forces acting on the person, one in this direction and the other in this direction, right? So what will happen is the person will neither accelerate in this direction, it will neither accelerate in this direction. It will accelerate somewhere in this direction, right? Somewhere in this direction. If this is a mass m, and two forces are applied on it, one in say this direction and one in say this direction, then the net effect will lead this particle to travel in this direction, right? Somewhat in this direction. Now, after visualizing this, we have the parallelogram law of vector addition, which says that the vector C, which is the resultant of A and B, or I can write it as vector C is equal to vector A plus vector B. This vector C is nothing but the diagonal of this parallelogram. If we complete the parallelogram, say this is O, this is P, this is Q, and this is R. If we complete the parallelogram and this vector is A, this vector is B, similarly, by the law of invariance of vector, I can write that this vector is B and this vector is A, because the parallel shifting of vectors is possible. So this is vector A, this is vector B, and this is the angle theta between the two vectors. So in that case, the parallelogram law of addition says that this diagonal will be the vector C, which is equal to vector A plus vector B. This diagonal will be the vector C, which is equal to the vector A plus vector B. That means this diagonal will be the net resultant vector of these two vectors, vector A and vector B, right? And we can also visualize this by assuming a small mass here, and if we assume that two forces are acting in this direction and this direction at an angle theta, then the resultant will be somewhere in this direction, right? Similarly, if I take another case, if these are the two vectors, vector A and vector B, if these are the two vectors, vector A and vector B, then this is the tail of both the vectors, the tails coincide here, and the angle between the two vectors will be this theta, where this theta is the obtuse angle. Now in this case again, if I visualize that, then I can imagine that if a particle is placed here, and two forces are acting on this particle, right? Two forces are acting on this particle, because vectors are nothing but, we can assume vectors to be force vectors. So if two forces are acting on this particle, one in this direction, one in this direction, the particle will have a tendency to travel in this direction, as well as the particle will have a tendency to travel in this direction. So the net effect will be somewhere in this direction. So again we can get this, how? By completing the parallelogram. We complete the parallelogram, and according to the parallelogram law of vectors, we draw a vector which represents the diagonal starting from the tail where the two tails coincide, starting from that point which is O to the opposite vertex. This will be the vector C, which is equal to vector A plus vector B. And we can also visualize this, that it will have a tendency to go here as well as here, and it will ultimately go in this direction. Now, trying to visualize more, if I say that this vector is of large magnitude, this vector is of large magnitude, and this vector is of a very small magnitude. Again, this is vector A and this is vector B. Now, again, I try to add the resultant, add and get the resultant of these two vectors, and what I feel is if I place a particle here and assume that these two vectors are the force vectors, or I can assume any vector, velocity, acceleration vector, assuming a force vector, then I can see that this force is lesser than this force. So the acceleration produced by this force will be lesser than the acceleration produced by this force. So the particle will ultimately feel the force more in this direction than in this direction. So the acceleration or the net force acting on the particle will be more in this direction than in this direction. So in this case, the resultant was in this direction. But what I feel is that due to large magnitude of force in this direction, the resultant force will be somewhat in this direction, So again, I check it by completing the parallelogram. I complete the parallelogram and draw the diagonal and check that my feeling was right? Because the magnitude is more, so the net force is tilted towards the vector B, right? If magnitude of A is more, say, and magnitude of B is less, then I can feel that the vector will be, the net force on the vector or the net vector will be more towards vector A. So by completing the parallelogram, I can check that the diagonal is tilted towards vector A more than vector B, right? So it's all about the field that we can get if we assume a particle and check the forces acting on that particle and visualize the net force which generally occurs to me, right? Knowing this, the parallelogram law of vectors says that if vector A and vector B are placed in this way such that their tails coincide and they are inclined to an angle theta, then the diagonal given in this direction will be the resultant vector, which is vector C, which is equal to A plus B. Now, there is another law called the triangle law of vectors. There is another law called the triangle law of vectors. The triangle law of vectors and the parallelogram law of vectors are interrelated to each other. The triangle law of vectors. Now, this triangle law of vectors, this states that, say if there is a vector A in this direction, in this part of the space, and say if there is a vector in this direction, in this part of the space. And let's assume that these two vectors are same as these two vectors, right? This vector is B and this vector is A. Assume these two vectors are placed in space in this manner. The triangle law says that place the two vectors in such a way that the tail of second vector coincides with the head of the first vector. The tail of second vector coincides with the tail of the head of the first vector. So, placing it in that way, we get like this, a situation like this, vector A and vector B. Now note, in this case we have two vectors like this, but in this case we have two vectors like this, right? So what I do is, I shift this vector B here without changing the magnitude and direction. We shift this parallelly here, so it becomes like this, it becomes like this, and this is also vector B. According to the property of invariancy of vector, that this vector and this vector will be same. So I can replace this vector by this, and now applying the addition law of parallelogram, the parallelogram law, I can say that this will be the vector C, which is vector A plus vector B, right? So this basically means the same thing. If I remove this, I see that the vector A plus vector B is the vector C in this way, completing the triangle. And if I look in terms of the parallelogram, I see that the diagonal completes the diagonal form will be the resultant of A plus B. Now, so seeing this, the triangle law says that if we have two vectors in such a way that the head of the first vector coincides with the tail of the second vector, then the vector starting from the initial point of the first vector and ending to the terminal point of the second vector right? Starting from the initial point of the first vector and terminating at the terminal point of the second vector is the resultant of both these vectors, right? This is the triangle law of vector addition. The triangle law and vector addition are almost the same, just we replace this here and replace this here, right? So these two laws were for the geometrical method to get the resultant of two vectors A and B. Now, taking some examples to find the resultant vectors. Let's take some examples. Let's say this is a vector A, let's say this is a vector C, and let's say this is a vector B, and we need to find the resultant of vector A plus vector B plus vector C, right? How to do this? We have three vectors in space like this, and we need to find the resultant of A plus B plus C. What we do is in these type of questions, what we do is replace this figure by this. Replace this figure by this. We can replace this vector A and bring it upon vector B, right? Because parallel shifting of vectors is possible. So I bring this vector A up over vector B, and now I can see that vector A and vector B lie along the same line, so I know that this will become vector A plus vector B, right? We just add these two vectors and get a long vector, which is vector A plus vector B, because vectors along the same line behave as scalars. Now this is vector C. Now from the triangle law, I can say that this is vector A plus vector B plus vector C. Simple, right? So this will be the net vector, or this will be the vector which produces the same effect as these three vectors would have been produced when placed in this manner, or when applied in this manner, or in this direction. Now, coming back, if I have this vector A, if I have this vector B, and the angle between these two vectors is theta, and if I complete the parallelogram and I see that this is the vector C, which is equal to vector A plus vector B. Geometrically, we can understand that this is the resultant of these two vectors, right? But since it is a vector and it's an important vector to us because it's a resultant of the two known vectors, we must need to know everything about these vectors. We need to know everything about this vector C, and for knowing everything, we need to know only two things, which is the magnitude of this vector C and the direction of this vector C. Now our job will be to get the magnitude of this vector C in terms of vector A, vector B and theta, and the angle produced by this vector C, subtended by this vector C with some reference point, right? So now, what I do is, for this purpose, I extend this vector A. Note, this is a very important derivation to get the resultant of two vectors A and B placed at an angle theta. I produce the vector A further, and I drop a perpendicular. Let's say this is O, this is P, this is Q, and this is R. I drop a perpendicular from Q to extended A vector, and let's say this is N. This is an angle which is pi by 2. Now, if this is vector B, then I can replace, or I can transform this here, and I can say that this is vector B, because the length remains the same as opposite sides of the parallelogram are of same length, and the direction is also same. So this will be vector B, and similarly this will be vector A. Now, our concern is to get the magnitude of this length and this length, right? I can see that this length will be mod B sine theta. This length will be mod B sine theta, because Qn upon Qp is equal to Qn upon vector B, which is equal to sine theta, right? So Qn will be mod b sine theta in terms of its magnitude. Similarly, using cos of this angle theta, say if this is angle theta, then this angle will also be theta. By corresponding angles, if this angle is theta, then this angle will also be theta. Now, ignoring this triangle and looking into this triangle, we can say that this is mod b sine theta and this is mod b cos theta. Because this upon this is sine theta and this upon this is cos theta. So this will be mod b cos theta and this will be mod b sine theta because this length is mod b. Right? As I told you, the magnitude of any vector is represented by modulus of that vector. Now, our task was to get the magnitude of this vector C. So applying Pythagoras in this triangle, in triangle ONQ, applying Pythagoras, I get modulus of C square is equal to ON square plus QN square, which is equal to modulus of A plus modulus of B cos theta whole square plus modulus of B square sine square theta. Right? Where this length is B sine theta, square is B square sine square theta, and A plus B cos theta is this total length. So A plus B cos theta whole square. This will be modulus of C square. Right? If I expand this, I get mod A square, I get mod B square cos square theta, and I have mod B square sine square theta here. So taking mod B square common, I get mod B square into cos square theta plus sine square theta, where cos square theta plus sine square theta is 1. So I can write it as mod B square. And I get another term which is 2 mod A mod B cos theta. Vector C square, modulus of C square. Right? We get B square cos square theta, and taking B square common, I get B square modulus B square into cos square plus sine square, which is 1. So I remain with modulus of B square. Now, modulus of vector C is equal to root over of modulus of A square plus modulus of B square plus 2 mod A mod B cos theta. This is the formula to get the magnitude of the resultant vector, to get the magnitude of the C between where theta is the angle between these two vectors A and B, and where C is the resultant of vector A and vector B. The modulus of C is given by root over of mod A square plus mod B square plus 2AB cos theta, where C is the resultant of vector A and vector B. Right?